Cartesian equation of a line, using direction cosines. Welcome, everyone. To begin today's lesson, let's take a moment to look at our topic, the Cartesian equation of a line using direction cosines. Now, if you have been following along with our previous lessons, you'll remember that we explored how to represent a line in three-dimensional space using what we call direction ratios. While those ratios are very useful, they aren't the only way to describe a line's orientation. In this specific subsection, we are going to move a step further and focus on a more precise and specific method for defining the direction of a line, using direction cosines. This approach will give us a very elegant way to write our equations, which we will dive into in the next slide. Understanding direction cosines. Imagine a line passing through three-dimensional space. This line isn't just floating randomly, it makes specific angles with our coordinate axes. Specifically, let's say the line makes an angle alpha with the positive x-axis, an angle beta with the positive y-axis, and an angle gamma with the positive z-axis. To simplify things, we take the cosine of each of these angles. These three values, cosine alpha, cosine beta, and cosine gamma, are what we formally call the direction cosines of the line. To make our calculations easier, mathematicians use a shorthand notation for these. We represent cosine alpha with the letter L, cosine beta with the letter M, and cosine gamma with the letter N, so you'll often see them written simply as L, M, and N. Now, there is one very important rule you must remember, which distinguishes these from the direction ratios we studied previously. Direction cosines are normalized. This means they are scaled in such a way that they satisfy a very specific identity. L squared plus M squared plus N squared must always equal 1. Keep this property in mind, as it will be vital when we derive the Cartesian equation in the next slide. Now that we've established that we can represent lines using direction ratios, let's move on to a more precise method, understanding direction cosines. The Cartesian equation. Think of it this way. If we know a specific point that the line passes through, and we know the exact direction the line is heading using those direction cosines, we have everything we need to uniquely determine the line's equation. To be precise, let's look at what we are given. First, we have a fixed point, which we'll call point A, with coordinates x sub 1, y sub 1, and z sub 1. Second, we have the direction cosines of our line, which we denote as L, M, and N. Now, here is the logical bridge. Imagine there is any other arbitrary point. Let's call it point P, with coordinates x, y, and z, that also lies on this same line. For point P to be on this line, the direction of the segment connecting our starting point, A, to this new point P, must be exactly the same as the direction cosines we've already defined. When we express this relationship mathematically, it leads us directly to the Cartesian form of the equation. It looks like this. X minus x sub 1, all divided by L, equals y minus y sub 1, all divided by M, which equals z minus z sub 1, all divided by N. Now that we have a clear understanding of what direction cosines actually represent, as we saw on the previous slide, let's see how we can use them to actually build the equation of a line. In the next slide, we are going to break down the step-by-step logic of how we actually derive this formula so you can see the derivation in action. Step-by-step derivation logic. Now, I know that seeing a formula like the one we just discussed on the previous slide might look a bit abstract. So, let's take a moment to pull back the curtain and look at the derivation logic. To understand why this formula actually works, we can follow a simple four-step logical process. First, we start with the basics, identify the point. We begin with a known fixed position in space, which we call x sub 1, y sub 1, z sub 1. This is our starting anchor on the line. Second, we need to define the displacement. Imagine we pick any other arbitrary point on that same line and call it x, y, z to find the distance and direction between our starting point and this new point. We calculate the displacement. This is found by subtracting our starting coordinates from our new coordinates, giving us the vector x minus x sub 1, y minus y sub 1, and z minus z sub 1. Third, we relate this displacement to our direction. As we learned in the earlier slides, the direction of our line is uniquely defined by the direction cosines. L, M, and N for our new point to truly lie on this specific line, the change in each axis, our x, y, and z displacements, must be proportional to these direction cosines. In other words, the ratio of the displacement to the direction cosine must be constant for all three axes. Finally, we form the equation. By setting these three equal ratios, the x ratio, the y ratio, and the z ratio, equal to one another, we arrive exactly at the Cartesian equation we saw earlier. If you can visualize this movement from a fixed point along a specific angular path, the formula will make much more sense. In the next slide, I'll give you a real-world analogy involving a laser pointer to help solidify this concept. Real-world analogy. Now, if all those formulas and variables feel a bit abstract, let's step away from the chalkboard for a moment and use a real-world analogy to visualize what is actually happening. Imagine you are holding a laser pointer and you have fixed it at a specific known coordinate in a room. Let's call the starting point x sub 1, y sub 1, z sub 1. This is our fixed point A that we discussed in the previous slide. Now, to hit a specific target across the room, you can't just point it randomly. You have to tilt the device at very precise angles relative to the floor and the walls. In our mathematical model, these specific angles, alpha, beta, and gamma, are exactly what determine our direction cosines, which we've labeled as L, M, and N. The actual path that the beam of light travels through the air represents our line in three-dimensional space. And the Cartesian equation we just derived? That equation is essentially a mathematical description of every single point that the beam of light touches as it travels from the pointer to the target. With this visual in mind, let's move on to a concrete, worked example to see how we apply this logic to a real problem. Worked example. Let's look at the problem presented here. Our goal is to find the Cartesian equation of a line that passes through the specific point 3, -2, 5, and we are given the direction cosines as 1/2, 1/2, and 1 over the square root of 2. To solve this, we will follow a clear 5-step process. First, step 1, we need to identify our given values. From the problem statement, we can see that our fixed point, which we call x1, y1, z1, is 3, -2, 5. And our direction cosines, L, M, and N, are 1/2, 1/2, and 1 over the square root of 2. Second, step 2, we recall the general formula we discussed in the previous slides. The Cartesian form is the fraction of x minus x1 over L, which equals the fraction of y minus y1 over m, which equals the fraction of z minus z1 over n. Third, step 3, we substitute our specific coordinates into that formula. When we plug in our point, notice what happens to the y term. We have y minus -2, and as we know from basic algebra, subtracting a negative is the same as adding a positive, so it becomes y plus 2. So, our equation now looks like the fraction of x minus 3 over L equals the fraction of y plus 2 over m equals the fraction of z minus 5 over n. Fourth, step 4. Now, we substitute the actual values for our direction cosines. This gives us the fraction of x minus 3 over 1/2 equals the fraction of y plus 2 over 1/2, which equals the fraction of z minus 5 over 1 over the square root of 2. Finally, step 5, we can simplify this expression to make it look much cleaner. Remember that dividing by a fraction is mathematically identical to multiplying by its reciprocal. So, instead of dividing by 1/2, we multiply the entire term by 2. For the last term, instead of dividing by 1 over the square root of 2, we multiply by the square root of 2. This leaves us with a much more elegant final equation. 2 times the quantity x minus 3 equals 2 times the quantity y plus 2, which equals the square root of 2 times the quantity z minus 5. Now that we have understood the theory and the logic behind the derivation, let's put everything we've learned into practice with a worked example. As we move to the next slide, I want you to pay close attention to the common pitfalls, because even with a clear process like this, it is very easy to make a small error in signs or substitution. common mistakes to avoid. First, a very important distinction. Do not confuse direction ratios with direction cosines. As we discussed earlier in the lesson, direction cosines, which we denote as L, M, and N, are normalized. This means they must always fall between -1 and 1, and the sum of their squares, that is, L squared plus M squared plus N squared, must equal exactly 1. If a problem provides you with direction ratios, which we can call a B and C, you cannot plug them directly into the denominator. You must first convert them into direction cosines by dividing each ratio by the square root of a squared plus b squared plus c squared. Second, keep a very close eye on your signs. This is where most students lose marks. When you are substituting your fixed point into the formula, remember that the formula uses subtraction. So, if your y-coordinate, y sub 1, is a negative number, the term y minus y sub 1 will actually become y plus the absolute value of y sub 1. For example, as we saw in our worked example, y minus -2 becomes y plus 2. Finally, watch your placement during substitution. It is easy to get distracted by the numbers and accidentally swap the positions. Always ensure that your direction cosines, L, M, and N, are placed in the denominators of the fractions and not in the numerators. Now, before we wrap up today's lesson, I want to pause and discuss some common pitfalls. Even if you understand the formula, these small errors can lead to incorrect answers in your exams. If you can avoid these 3 mistakes, you will be well on your way to mastering this topic. Let's move on to our final summary of the key takeaways. Key takeaways. First and foremost, remember the main formula we've been working with. The Cartesian equation of a line using direction cosines is x minus x sub 1, all over L, equals y minus y sub 1, all over M, which equals z minus z sub 1, all over N. This is your fundamental tool when you know both a starting point and the specific direction of the line. Second, keep in mind what those variables L, M, and N actually represent. They aren't just random numbers. They represent the cosines of the angles that the line makes with the x, y, and z axes respectively. This is what gives the line its specific orientation in 3-dimensional space. Third, there is a very important mathematical property you must always check. The condition L squared plus M squared plus N squared equals 1 must always hold true for direction cosines. If you are ever working with direction ratios instead, remember that you'll need to normalize them so that this identity is satisfied. Finally, remember that this specific form of the equation is particularly useful in problems where the orientation of the line is given to you in terms of angles rather than just ratios. All right, we have reached the end of our lesson, so let's wrap everything up by reviewing the key takeaways from today's session. I hope this summary helps solidify your understanding. If you have any questions about the derivation or the worked example we went through earlier, be sure to review those slides. Great job today!